It's already introduced, but as mentioned, I do like sharks, and this is one of the shark murals here around Toronto. Today, I'll be talking generally about hidden Markov models in ecology, the different applications, and some of just the foundations and fundamentals of what a hidden Markov model actually is. So we'll start off with a brief introduction. And first off, also think about, well, what type of ecological data is amenable to analysis via hidden Markov model? So there was a great session by Theo Michelot, which I should mention here as well, on animal movement, where he covered some hidden Markov model packages for analysis of GPS data. You can also apply hidden Markov models to acceleration data, dive data, and so on. And what these different types of data streams have in common is that they're typically are collected over time at regular intervals. Right, so we can think about having a position for a specific animal collected every 5 minutes, every 10 minutes, or so on, or in such a way that it can be filled if there's any missing data. With acceleration data, typically have fine scale acceleration data collected possibly 20 hertz that can be summarized in terms of 1 second intervals, or every few seconds having some metric that can be used as a proxy of energy expenditure or just activity levels in general. And we'll actually look at some corpus type data in a bit. So this is generally where I tend to work. So I tend to work in applying hidden Markov models to animal movement, but we can also apply hidden Markov models to occupancy data. So the presence, absence of a species over time. So we can think about, we go to see if we can find this animal in a certain location, and maybe at time t, they are present, but the next time point, which could be a month from then, a year from then, it could be absent. So you might want to understand, well, what happened in between? Maybe at the next time point, they are present. So there's some sequence of the presence, absence patterns over time, and this can be described with the hidden Markov model as well. And with capture recapture, there is an initial capture event, followed by subsequent recapture events. And so in general, when we talk about applying hidden Markov models to ecological data, we want data that is collected not necessarily just over time, but in sequence. And so big picture, we're talking about sequential data. And this is typically time series. So it doesn't always have to be. We're just trying to describe any phenomena that has a certain ordering in occurrence. So hidden Markov model is composed of our observation process, and this can be presence, absence. It could be something for animal movement, and so on. And we have, of course, a process occurring in sequence. And what's different about a hidden Markov model is that we also care about a latent state process. So this is the general graphical structure of a hidden Markov model. And what the state process provides is some ecological interpretation of phenomena that we're interested in. So for example, we can collect GPS data, but perhaps what we care about is not necessarily their positions over time. What we care about is their actual behavior. So we can try to use the data we collect to inform some latent process that we cannot observe. And I'm going to talk about specifically how this is actually applied to each of the 3 different categories that I mentioned before. So formally, hidden Markov models, often denoted as HMMs. And if you'll be at ISEC this summer, you'll likely see a lot of talks on HMMs. So formally, it's a doubly stochastic process composed of an observation process. This is the data we can collect. And an underlying latent state process, which we try to infer. And mathematically, we take it to be a Markov chain. Our observations can be discrete, continuous, measured with error, multivariate, or could even be extended to an ARP process, where we typically refer to hidden Markov models with autoregressive processes as Markov switching models. And this has actually been used as well to analyze depth data. So Markov switching models, hidden Markov models refer to generally the same type of class structure. Our latent state process is a discrete random variable, meaning specifically here, it can take on the values 1, 2, n. So at each time point, zt, this is equal to some fixed integer value, where n is in 1 to n. And generally, the 1 to n corresponds to the different latent processes of interest. So how many different latent processes are occurring in our time series or sequential data? And formally, in HMM literature, this is referred to as the number of states. And so the essence, the high level, there's a mathematical description, which is number of states of a hidden Markov model. And the general interpretation in ecology is what are the number of processes of interest? For example, for animal movement, this could be the number of behaviors we hope to identify. So if we have n equal to 2, and we fit a hidden Markov model with 2 states, we might think there's 2 behaviors exhibited in our time series. We also have the state-dependent distributions, which describe how the data are generated in each state. So we have different probabilistic structures for each state. So when an animal is in state 1, exhibiting behavior 1, that might refer to, for instance, maybe resting versus traveling behaviors in terrestrial animals, where resting, they're not moving very much, versus if they're traveling, they're moving quite far. And here, the state-dependent distributions will then be very distinct to describe the movements associated with resting behavior versus the movements associated with traveling behavior. In resting, the animal is likely not to move positions very far. And when it's traveling, it's going to move much further distances. We have a transition probability matrix, which has entries, the conditional probabilities, the probability of z sub t equal to j, given z sub t minus 1 equal to I, which describe the state switching dynamics across these different processes of interest. So how do we switch from resting to traveling to perhaps a third behavior, such as foraging? So what is the sequence of events that typically occurs? And lastly, we have the initial state distribution, which has entries, probability of z sub 1 equal to I. So what is happening at the first observation? What's the first process we observe? And generally, we try to infer these latent states. So one of the nice things about hidden Markov models is that there's these so-called state decoding algorithms for hidden Markov models, which means we can connect observations to latent states. So akin to clustering via k-means or other types of machine learning algorithms, HMMs can do the same exact thing. We can connect an observation to a different state, which is nice when the latent states correspond to something ecologically meaningful, because then we can identify which observations correspond to different, for example, behaviors in animals. There's 3 general ways of doing so. We have the Viterbi algorithm, which computes the most probable sequence of states that generate the data. We have the forward-backward algorithm, which computes the marginal probability of the state at time t. So what is the most likely state at each time point? And then we also have the forward filtering backward sampling algorithm, which samples from the joint distribution of the state sequences. And it will produce the way to simulate entire state sequences that could have generated your data. Most often in the packages such as Move HMM and Momentum, you have Viterbi and the forward-backward algorithm. And today when we use Stan, we'll be able to generate these sequences as well. So sometimes just learning about a mathematical structure, it's difficult to understand, well, what type of process am I actually modeling? And I think the most important thing when learning any statistical model is understanding what type of data does it actually generate. So let's simulate from a 3-state hidden Markov model, which means we set our n equal to 3. And now, given we have 3 states, there are 3 probability distributions that generate our data. Each of them have a normal distribution. So state 1, the data is generated according to mu 0 and standard deviation 0.3. The data are generated according to a normal distribution for state 2 with a mean of 2 and standard deviation of 1. And in state 3, our data are generated according to a normal distribution with mean 5 and standard deviation 3. So a hidden Markov model in particular is a class of mixture models in which there's dependence over time. This is why we have our different components. Our initial distribution, so what occurs at time 1, we take it to be each of the states equally likely. And then transitions from state 1, state 2, state 3. So if we are in state 1, what is the probability that we'll switch to state 1? That's 0.8. So generally, the transition probability matrix is best read as rows. So given that you're in state 1, what is the probability at the next time point you'll stay in state 1? That's 0.8. What is the probability that you'll switch to state 2? That's 0.1. And with probability 0.1, given you're in state 1, time t, you'll switch to state 3, and so on. And similarly for each row. So it provides probabilities of how we switch over time between states. And if you'll notice, here, they sum to 1. So each row is going to need to sum to 1. And that describes the evolution of our underlying Markov chain. So if we generate, say, 2,000 observations, we look at the first 500. We have our gold state, our blue state, and our green state. And what's noticeable about this process is that if hidden Markov models, again, are these mixture models with dependence over time, which means that as soon as we have one gold observation, we're likely to produce multiple gold observations in a row. So this is one of the key ideas behind hidden Markov models, is that there is persistence in these processes that occur. So for example, if an animal begins to rest and we collect data every 5 minutes, there's likely to be persistence in that resting behavior over time. An animal is likely not to rest in the 5 minutes, travel 5 minutes, forage 5 minutes, rest 5 minutes, and switch very quickly between these behaviors. Right? So we want models that actually capture that realism. So once we enter our green state, we'll have a few green observations in a row, possible switches to a blue state. We'll have a few blue dots in a row, and so on. All right, so we want to simulate the sort of bursts of observations in each state. And that's key for the hidden Markov models, and a key reason why they're so applicable in ecology as well. Now, if we remove the temporal component and we just look at a histogram of the data and overlay the different densities, what we'll see is that typically it's going to be, not necessarily doesn't have to be, but it's often multimodal, meaning it's pretty evident that there is something going on here, then perhaps something else here, and then there's some extreme values that are unaccounted for. So we have the gold state, the blue state, and the green state. And these generate the data that we see. So in a hidden Markov model, when we apply it to ecological data, we care about capturing the temporal structure, which means how many observations from each state are we likely to see before we switch. So what is that persistence over time? And we also want to capture the so-called marginal distribution. We want the gold, the blue, and the green state to capture the histograms. So quickly, what does a hidden Markov model then look like for animal movement? So today we'll look at some porpoise dive data. And this data is from multi-scale modeling of animal movement and general behavior data using hidden Markov models with hierarchical structures, a long title, but particularly from Flores van Beest and Jacob Nielsen. So this is a data set that they contributed, and thankful to them for doing so. And one of the things they measure per dive is the dive duration. And modeling dive data is a bit interesting because with GPS data, for example, you might have a position every so often. So every 5 minutes, every 10 minutes, and so on. But dive data is simply the animal producing these different dives, right? And I'm in no way a biologist, so hopefully that's somewhat realistic. And so what people tend to do is that we have this time series of the depths at which these animals are. And rather than focus on switches over time, they segment the time series into different pieces. So we have one piece here, one piece there. So this is one dive. This is another process. This is at the surface behavior. Then we have our third smaller dive, again at the surface. And so they segment the time series. And now what we're modeling is a sequential process. And there's a certain dive duration associated with that sequential process. So this is, again, one of the slight ways that you can actually process your data. So you have sequential processes over time without it necessarily having to be every 1 hour, every 5 minutes, every so often. So we set up the hidden Markov model. What does that mean in practice? Well, we need to define the number of states. And this is one of the most difficult aspects of fitting hidden Markov models to animal movement data, but it's something that Théo Michelot covered in his presentation. And he made reference to a great paper by Jennifer Pohl. So the number of states, however, in practice, you typically start from, let's say, n equal to 2. And in subsequent iterations, you can increase the number of states, and you can assess how well the model captures your data and the process of interest. State-dependent distributions. The dive durations are integer valued, so we can turn to something like a Poisson distribution. But these are also choices that we're going to have to make. Do we select a Poisson distribution for our state-dependent distributions? Do we select a negative binomial distribution? Right, so what are the correct distributional forms for our states? And that's very challenging, but it's always just an assumption we need to make going forth. We have a transition probability matrix. So we have the transitions between state 1 to state 1, from state 1 to 2, from 2 to 1, and 2 to 2. And we have an initial state distribution. So when we set up a hidden Markov model for animal movement, these are the choices that we have to make. Now, on to capture recapture. So when we're modeling capture events, we can do so via an HMM framework, where in the most simple way, we can just say that an animal is either alive or it's dead. And the observation process is the animal seen or is it not seen? And taking inspiration from a graphical structure I saw in one of Olivier Jimenez's presentations, we could think about, let's say if the animal is alive. We don't know if it's alive or it's dead, but the latent process is that it's actually alive. We can, if we have 3 different measurements, in one case, we can have a 1 for it was seen. Now, what happens if we do not see it? So the idea behind incorporating an HMM into capture events is that an animal might be seen, but it's still alive. It's possible that it wasn't seen, but it's actually alive, because there's some detection probability associated with actually being able to see the animal. So with probability P, we will see the animal if it's alive, and probability 1 minus P, we will not see the animal if it's actually alive. So the key piece in fitting hidden Markov models to capture recapture data is really in the zeros. So if it's 0, is it actually the latent process corresponds to it's dead, and that's why it's not seen? Or is it not seen and alive? So really the zeros are a big process, big part of understanding what's actually occurring. So what does our setup look like? Well, in the most simple case, we'll have 2 states referring to the animal is alive or it's dead. And if it's alive, with probability 1 minus P, we won't see the animal. So there will be a 0 in the data. And with probability P, we will see the animal. Right, so the zeros here is not seen, and this is seen. So recall that the state-dependent distributions tell us how the data are generated, and our data here are just going to be sequences of zeros and ones. Now, when it's dead, we assume that we're not going to see it with probability 1. And with probability 0, it's not going to be seen. So that is how the data are generated in the setup. The transition probability matrix structure is also different from animal movement in that there's a probability of survival. So the probability S that we want to estimate that describes the transition between alive to alive. Recall this is alive. And with probability 1 minus S, the animal will go from alive to dead. And what's different, of course, is that it cannot be resurrected. So once it's dead, it stays dead, it's forever dead. Will not transition to alive. Right, so this one is associated with once it's dead, it will only transition to the death state. Formally, this is referred to as an absorbing state. And when I mean formally, is when we talk about Markov chains. So death is an absorbing state. And the initial state distribution, while it's something we want to estimate for animal movement, in this case, if you start with we'll start with an alive animal, right? It was captured. We're assuming it was captured alive, not captured dead. So the state process we know at time 1 is alive, does not start in death. So we can already see some slight differences from how we apply hidden Markov models to capture versus how we apply it to animal movement. You can also increase the number of states where you can have different number of alive states or different states that correspond to different phenomena as well. But there's typically only one death state. I should say typically. I say typically because I don't do capture-recapture. Okay. Now, there's also hidden Markov models applied to occupancy data. So with dynamic occupancy models, we take the state process in a simple framework that is occupied versus unoccupied. So it's either present or absent. And the observation process is similar to the capture-recapture in that it's detected versus not detected. And a key criteria is that a species can occupy a space yet not be detected. So similar to the capture-recapture, we have 1 is that it was detected, and 0 not detected. So if we have a 1, it was detected, meaning that it's occupying that space. We have a 0 telling us that it was not detected, but still occupying that space. So with probability P, it will be detected, and probability 1 minus P, it will not be detected, even if it is occupying a space. And the transition from occupied to unoccupied is referred to as extinction. And once it's unoccupied, the animal will not be detected. And so again, in large part, we're interested in these zeros, because these zeros in our time series can be that the animal is actually occupying that space, or that it was not occupying that space. And so what we need to define here is the number of states, which we can start with just 2. And similar to before, we have the unoccupied state and the occupied state. If the space is unoccupied, then this is the not seen or detected. We'll only see zeros, because if it's not there, we won't see it. If it's occupied, with probability 1 minus P, we won't detect it. With probability P, we will detect it. In the transition probability matrix, rather than the capture-recapture, we had a 0 and a 1. Here we allow for transitions between extinction and colonization. So it can go from occupied to unoccupied and unoccupied to occupied. And there is a chance that at the first time point, the species is actually occupying the space, but it was not detected, unlike the capture recapture. So we'll want to estimate it. So HMM nuances. So one of the big things is, do we have state labels? So in general, you can apply a hidden Markov model to the sequential data in ecology without actually having any sort of ground truth for the state sequences. So for animal movement, incorporation of state behavior labels has not necessarily been thoroughly studied in a mathematical sense of what do we gain if we actually see the animals foraging and we label part of the time series as foraging. But it is possible to assume that some or all of the state sequences observed. So if you know the states, for part of the time series at least, there's ways to incorporate that information. For capture recapture, observing an animal tells us that the animal is still alive, such that the state is known. But when we do not see an animal, there is uncertainty as to its true state, whether it's alive or dead. And for occupancy, as with capture recapture, we have the state if the species is detected, but not if it is undetected. And how do we evaluate those models? So unsupervised versus supervised is sort of more machine learning terminology of unsupervised being we only have the observations. We don't have any underlying state sequences. And typically this is how HMMs are used in animal movement with the move HMM package or momentum package. And supervised typically refers to having data that has both animal movement or some other ecological process, and we have the underlying state sequences. So we know exactly the types of behaviors that the animal was exhibiting. But really the big thing with HMMs is, do we care about explaining the data generating process? Or do we care about predicting the states correctly? And those are actually two related but fundamentally different objectives. And the reason I say this is because misspecified models, so models that are not good data generating mechanisms, they could predict the states just as well as the correctly specified hidden Markov model. So if you have two competing hidden Markov models and you get the same types of state predictions, it doesn't necessarily tell you anything about the data generating mechanism, but it just tells you that these two models can predict the states similarly. And when there are no state labels available, we're generally building an HMM that captures the data generating process, which is assess via residuals, model selection, simulation, with no guarantees that the states correspond to meaningful processes. Because if we can't validate our states, we can't assess how well the model captures those behaviors. And this is something very subtle, because in the literature, we often say, well, hidden Markov models are used to identify different animal behaviors without ever actually validating that the states correspond to meaningful behaviors. So this is where a lot of domain expertise comes into play. And we know that different patterns are generally only seen when an animal is behaving in specific ways. At the same time, it's just something good to keep in mind. When we interpret our states as ecological processes, are we validating it with ground truth, or is it an interpretation that we're providing? So today we're going to fit some Bayesian hidden Markov models. And of course, once we go Bayesian, we need to set priors. So setting priors distinguishes a Bayesian framework from a frequentist framework because it's necessary to quantify the uncertainty of our parameters in a probabilistic manner. So what do we need from an HMM for it to work? So for animal movement, where we don't have specific ends, we usually want the transition quality matrix to be full rank and ergodic. And the key thing is we want the state-dependent distributions to be distinct. So we can set priors that a priori assumes that our state-dependent distributions are different from each other. For example, by specifying perhaps mu1 is a normal distribution with 0, 1, and mu2 is a normal distribution with mean 5 and standard deviation 1. So a priori, we can assume that our means are different from each other. So helping the model with what we know it needs. Okay. So time to fit some Bayes and Hidden Markov models. And these slides are also available on GitHub. And a few references as well. But I would also encourage you to go again to Teo Michelot's presentation on animal movement, because he also covers Hidden Markov models and provides some good resources. Okay. So I think I have maybe about 15, 20 minutes. 15 minutes, 10 minutes.
Yeah, it's fine. You can take 15 to 20 minutes. That's great.
Okay. Okay, so we might not get as far as we could have, but there's a few things in the GitHub repository. And what we'll start with is simulating from a hidden Markov model, which is really the big thing. Beyond just, there you go. Beyond just fitting hidden Markov models, understanding the types of data that different parameters simulate provides really good intuition into if this is actually useful for your process or not. So we'll simulate the data from a hidden Markov model. We specify the number of states, the state-dependent distributions, the transition probability matrix, and the initial state distribution. So we start with specify the number of states. I want just 2 for now. The initial distribution is 0.5, 0.5, meaning with equal probability, this process will start in state 1 versus state 2. We'll have our transition probability matrix. So if given that we're in state 1, with 90% probability, we'll remain in state 1, and 10% probability, we'll switch to state 2. Given that we're in state 2, with 1% probability, we'll remain in state 1, or we'll switch to state 1, sorry, and with 99% probability, we'll remain in state 2. So given that this is 0.99 versus 0.9, what we're going to expect is that there's a longer persistence in state 2 than there typically is in state 1. So we'll have longer bouts of state 2 versus state 1. And we're going to generate data from normal distributions. So in state 1, we'll have mu equal to 5 and standard deviation of 2. And in state 2, we'll have a mean of 10 and a standard deviation of 1. So let's generate 500 observations. Just generating vectors where I'll save the states and save the observations. So for the first state, and this is generally how we begin to simulate from a hidden Markov model, we start with the state process. Because given the state process, then we know how to generate the data. So the first observation, we want one draw from a categorical distribution with probability, the initial state distribution. So if we do sample, this gives us samples of 1 or 2. Now we can see, where are we starting? I'm starting in state 1. You might be starting in state 2. Now, what happens at time 2, state 2, depends on the state at time t-1. So we're incorporating that information into how we generate the data. There's this sequential process. So we can see maybe the first 10. So I'm beginning in state 1, and then I remain in state 1 and remain in state 1 for a period of time before I switch to state 2. And I imagine that if we see a few more, we're going to see we remain in state 1 for a period of time. Then we switch to state 2 for a very long period of time before we switch back to state 1. So typically, when we think about how we generate data in this transition probability matrix, people often think, well, at each time point, we're making a decision if we switch states or not. So that might make you think that we can rapidly switch between states. But with a high enough diagonal values, 0.99, 0.9, what we're actually going to see is that we generate sequences of state 1, sequences of state 2, and so on. So it's not this rapid switching behavior. And for the observation processes, we want to generate for first time point, we start in state 1. And so we generate data from the normal distribution with mean 5 and standard deviation 2. Okay, so if we look at this vector, maybe just the first 10, what this tells us is that the first observations are generated according to a normal distribution with mean 5. And then once it switches to state 2, the data are generated according to a normal distribution with mean 10. Okay. So you can visualize the simulated observations. Right, so we have the peach and the blue observations, where we see that the first few observations are generated according to state 1. And then we have a lot of blue. There are some switches back and forth, right? But recall that our persistence from going, once we're in state 2 to remain in state 2 is 0.99. So that means we're going to have a lot of observations according to state 2 in a row. This is what our data is going to look like. You can also visualize the states. So we have the observation process. We can connect it with the line, our time series data. And what I would encourage you to do is to modify. So you can go through and modify the means. You can increase the number of states. And you can also change it to state-dependent distributions. So rather than R norm, you can have R gamma or R plus, to generate data from a Poisson distribution. And plotting the state sequence, what we're going to see is that, again, when we're switched to state 2, we're in state 2 for a long period of time. And once you change the parameters, once you lower the dependencies, once it's not so close to 1, 0.99, there'll be more rapid switching between the two. Another thing that's quite important, which again refers to how we switch back and forth between the states, is that it's not just at each time point we make this decision without any regard of what's happened. There's a so-called state dual time distributions for hidden Markov models, which is more applicable for applications to animal movement, where we have these long processes occurring over time. And it tells us the number of times we expect to stay in state 1 versus state 2 before we switch. So with probability 0.3, we'll spend one time point in state 2 before switching, and so on. So these are geometrically distributed state dwell time distributions. Then, so that is just how you simulate data from the hidden Markov model, some of the key aspects. And lastly, you can get into the animal movement RMD file. Okay. And for this, you can load in tidyverse, Liberty just for some date time. And I'm going to show you command stand R. So stan is a software that's principally used for Bayesian inference, although not necessarily just for Bayesian inference. And command stand R is one of the R packages associated with it. And they've recently updated it to include some automated HMM functionality that's helpful in terms of simulating from the state sequences and predicting data. So we'll load in the purpose data from this paper. Can process it a bit. This is the plot we saw earlier with dive durations over time. So we notice here, there's a period of time when the porpoise is diving for longer periods. We can make it a time series. Let's look at the data specifically. So we have the date time of when the dive began, and we have dive duration. There are also other variables associated with this data set, like maximum depth, as well as dive wiggliness. Right, so we could construct multivariate hidden Markov models. So to set up our model, we write some stan code. So this program uses command stan. So if any of you have used stan before, what people typically do is they write the stan function, some stan code, and they'll check. Is my code syntactically correct? And you'll notice that there's all these errors. There's a message from parser. It says it doesn't know what HMM marginal is, which we'll discuss in a second. This function isn't found, it doesn't like it, and so on. So there's all these error messages here, which you'll have to disregard. Because we're using command stan, the HMM functionality is only in command stan and isn't in R stan. So if you try to check if your stan code is correct, it's going to tell you that it's not, but it actually is. So stan code is written in blocks. You have a data block, where it's the information that we're going to provide to the model. So we're going to specify the number of states, specify the number of observations. We denote that our observations are integer valued, which we need to do if we want to model it via Poisson distribution. And then we'll have some prior values for the lambda values, the lambda parameter of our Poisson distribution for each state. We want to estimate the transition probability matrix. We want to estimate the state-dependent parameters. We want to estimate the initial state distribution. Now, this is the key thing that's different in command stan R. So we have transforms parameters, which means that we need to actually construct certain matrices. Log omega refers to a matrix where we evaluate the observations under the different Poisson distributions. And gamma is our transition probability matrix transformed, or transposed, sorry. So our theta here is a simplex. And the way that stan needs this information is it needs the transpose. Okay. So our model is actually quite small compared to HMMs written in just stan code. We just need to specify priors for our state-dependent parameters. We could also specify priors for the initial state distribution or the transition probability matrix. Here, I'm leaving it empty and a priori assuming something flat. And the key difference from command stan R and R stan is that all we need to do is write HM marginal. We input log omega, gamma, and initial distribution. Okay. So a lot of the setup is here in the transform parameters block. And one of the reasons to use command stan R and the increased HMM functionality is that we can extract matrices of state probabilities So this is from the forward backward algorithm. And we can generate posterior distributions of our entire state sequences. Right, so we have state spread using HMM latent RNG. So some of these functions, HMM underscore hidden underscore state underscore probability prob, and HMM underscore latent underscore RNG. And then given the states, we can generate data for use in a posterior predictive check. Okay. And so remember, you're going to get an error if you decide to check your code. And one thing I hadn't mentioned yet is we know our lambda has to be greater than 0. There's ways to assign some ordering. So let's run this code without just describing any ordering and see what it gives us. So we first compile the model. And yes, we're doing live Bayes. And it's going to give you all these different warnings. It's okay. So right now it's compiling, and it shouldn't take too long. Or maybe I jinxed myself by saying it shouldn't take too long. There we go. Whew. So in order to pass data into Stan, we want to create a list where we have y equals dive duration, n equals 3 states. Here I'm starting with 3 states. T is the number of observations. I'm just double checking T. And then these are quite horrible priors for my scale and shape. We could change this. And actually it's going to be, I'll update the code on GitHub, but this is actually the rate, not the scale. And to sample from our posterior distributions, we use the Porpoise HMM, the compiled Stan model, $sample. We give it the data, the number of chains, and the number of parallel chains. We want to sample from the posterior distribution of all our parameters in a parallel fashion. Change this to beta. Okay, hope some of you are running this model as well. You can all see what it comes up with. And okay, we're sampling. You can take a quick look at some of the messages that you're going to see. So this often happens to me when I start sampling from the posterior distribution. It tells me it's rejecting the initial value. So this happens. It's nothing necessarily to be too worried about. If it rejects all of your initial values, then we definitely want to worry. But it might reject a few, and that's okay. There are parts of the parameter space where an HMM is not well behaved. And so we have this log probability issues. And the longest time will be spent in the Solmar period. Although maybe with the extra constraints of being on Zoom, it will run a bit slower. Ooh, okay. Okay, running Bayes live was a risk. We knew it would be a risk. And as all good Bayesians will say, no, it runs a lot faster. It's just something happening right now. But what we're actually getting from this model is we're not only getting posterior samples from our parameters, we're also getting all of these different state probabilities and posterior state sequences. So it's drawing a lot of information. Yeah.
Vianey, would you like to go over some of the questions while we wait the model to generate the samples?
Yes, definitely.
Yeah, all right. So I'm looking at poll everywhere here. There's a question: can you take into account knowledge in the transition process? So behaviors may change with time of day or season. Extinction and colonization may change with environmental covariates. I assume that you can add this in theory, but how hard is it to do this in practice?
Okay, great question. So this is one of the most appealing parts of hidden Markov models and what we really don't have too much time for today. But that is exactly why they're so useful, because we can incorporate this covariates into the transition probability matrix, into the state process as well. And typically we do it via, just like we transform just GLM link functions. So in our transition probability matrix, if it's just a 2x2 matrix, what you'll have is a logistic regression in each row. And so Theo Michelot actually did cover incorporating covariates into hidden Markov models in his presentation. But certainly it's exactly why HMs are so useful, that can not only uncover this latent state sequence, but we can incorporate external information to examine drivers of these different processes.
Great. There's a question here. Are there any tips for identifying correct states if state-dependent distributions for all unique data streams are greatly overlapping or only varying dispersion? So maybe they have the same mean, but different standard deviations. So do you have any tips in relation to identifying correctly the state if there's so much overlap? And I think the other sort of, it's the same question, but do HMMs incorporate covariance among state-dependent distributions?
Okay, great. Thank you. So in theory, hidden Markov models, you can apply them even if there's a lot of overlap between the distributions. And it really depends on what are your interpretations of those different states. So in some cases, I think more like economics, you might have a process that has been where you might really just care about the amount of stochasticity over time. And so you'll model some processes and there's a lot more stochasticity. In other cases, there's periods of less stochasticity and less change over time. And so you can have a lot of overlap where the dispersion is quite different over periods, and that reflect a different state. But of course, if ecologically that is not meaningful to what you want to do, there's ways to specify different state-dependent distributions, or part of it might just be that the information isn't in the data. Right. So one of the big parts of even fitting hidden Markov models is processing the data correctly. And I say correctly very loosely. But what distinguishes, if you want to capture specific behaviors, what are some of the features that really distinguish those processes? And then the second one was
about incorporating covariance among state-dependent distributions.
Right. So that can be quite difficult. And typically it's difficult, for example, if you have non-continuous data. So if you have continuous data streams, we might look to model the state-dependent distributions with multivariate normal distributions. And then it has a covariance structure already embedded. We can also extend it to model via what's called copulus. And this is where we can incorporate dependence between the different data streams. But typically what people do is that they have a state-dependent distribution for each data stream. That's called contemporaneous conditional independence, where within a state, we assume that the data streams are independent of each other.
All right, great. Is it possible to use a model selection approach to define the best number of states for your data? So let me see. It's saying running multiple HMM accounting for different behavioral states in each, and then run a model selection analysis. So I guess something like AIC, BIC maybe?
Mm-hmm. So there's a paper by Jennifer Pohl, which is selecting the number of states in a hidden Markov model, something along those lines. And I can link to that in the chat in a sec, where she has some practical considerations of selecting the number of states. And generally, AIC and BIC is going to lead to too many states. So you might end up having a 7-state hidden Markov model preferred. Yet those 7 states you can't interpret in any ecologically meaningful way. So it's a balance between what is the ecological question that you're trying to answer and what features maybe a 5-state HMM can't capture that a 7-state HMM can. And typically these are small things in the data. But it's kind of like if we just incorporate more and more states, it's like an arbitrary inflated high R squared in our linear regression. Of course, we can incorporate, just put more and more and more in, and we'll get a better fit. But it's not necessarily a better explanation of what's actually happening. So use AIC and BIC with caution.
Yeah, the other thing that I was also going to add is that there are some approaches like a state breaking prior, things like that, that can enable you to determine the optimal or perhaps a kind of what would be the ideal number of clusters, kind of in regular mixture models. I'm not sure if people have experimented with that in Hidden Markov model, but if people are interested, I'll add a link, I'll add the name of the article that does something along those lines.
Yeah. And one thing to note also, I mean, this is going to be for any type of clustering algorithm, is that say you identify that there's 3 important clusters or 4 important clusters. Once you add in more data, you're likely picking up different processes that you were observing in that first data set, and you might have to increase. So there is this notion that there is a chance that depending on how fine scale your data is, depending what you've observed in different data sets, it might not just be that there's 3 and there's only going to ever be 3 states.
Mm-hmm. Yeah. And so, Vianey, you mentioned 3 algorithms like Viterbi, forward, backward algorithm, etc. Is one algorithm appropriate to a particular type of data? How do you go about deciding which of these algorithms you want to use or you want to rely on?
So I think if you're using HMM and momentum and you don't want to code something up yourself, you'll choose between the Viterbi algorithm or the forward-backward algorithm. So at each time point, you're either going to have the most likely sequence of states that generate the data, or at each time point, you'll have probabilities associated with each state. So observation 1 with 90% probability was generated according to state 1, maybe 10% probability generated according to state 2. Right, so you have some uncertainty associated with what states generate the data. I think embracing uncertainty is the best, because your most likely state sequence doesn't tell you how actually likely it was over other possible state sequences. So the Viterbi is great. The Viterbi makes life easy because we just have a single answer, and it's nice. It tells us exactly this is the most likely thing to have occurred. Of course, it can also hide a lot of information. Right? So how likely was it actually that that observation was generated according to that state? How certain are we? So I think embracing uncertainty causes more challenges, but I think using the forward backward at minimal is better than using the Viterbi if possible.
Great. What is your perspective or your suggestion in terms of how to better incorporate knowledge about observed states in STAN?
So that's quite an. I thought I knew the right answer last year, and so I had a few students work on a project where we had horn shark accelerometer data, and then we have videos for those horn sharks because they're in the lab, and we had the horn shark foraging on an urchin, foraging on squid. It was swimming around, and we thought, great, we're going to incorporate those state labels and then fit a hidden Markov model, and we'll produce these better state predictions. Like if we leave one of the time series out, we'll be able to predict the behavioral states correctly. And it ended up, it's harder than you would think. That's what I naively thought, that we could just incorporate these states, incorporate behavioral labels. But there was, I think, a mismatch between how we specify the state-dependent distributions. And we ended up with a lot of computational challenges that I'm actually still working on today, and some of my students are still working on. So naively, you just put in these observations generated according to the state. In practice, it might be take a little more nuance between also using the states, the behaviors that you observed, looking at that data, and then trying to think what state-dependent distributions are the best for my data as well. Just something at least nice. You can, instead of just speaking normal distributions for all the states or gamma distributions, you have some information to inform you on the actual structure, the probability distribution of your states.
Mm-hmm. Mm-hmm. All right. Are dynamic occupancy models applicable to sampling designs where you can't identify individuals, like camera traps?
That is a fantastic question, but not one I think I can answer. There are people that do work on dynamic occupancy models. I would think Krishna at least knows way more about this than I do.
No, I mean, again, yeah, there's a lot of people that have been working on this pretty specifically, and so I don't think I can really add much to it. This isn't quite my area right now.
Okay, so, I'm going to take.
So we can continue with the questions, or I don't know if you want to show continue now that it has generated the samples and continue presenting.
Yeah. Actually, it might take a little longer now. Naturally. My poor little laptop is trying, it's going. I can maybe continue with the questions.
All right, let's do that then. How do you determine the distributions to use? Do we need to assume the states and look in the literature for their distributions?
So there's a mathematical way to, well, you start off first with what is the structure of your data, right? So is it defined on the positive real line? Is it defined on the real line? Is it integer valued, and so on? So first step is just making sure that whatever distributions you choose they correspond to the domain of the observations. Secondly, it's in practice, I would say that some of the first HMM applications that I really read about were applying to GPS data. So telemetry data, you have a GPS observation. And I noticed there's two groups. One that models step lengths via Weibull distributions, and the turning angles are, it's a Cauchy, I think. And then you have another group that does gamma state-dependent distributions for step lengths and von Mises. So I, let's say, grew up on the gamma and von Mises, and I've sort of hung around there. So this is where the distributions that I use for step length and turning angle. And then I have collaborators that use Weibull. So what are the best things you could do? It's probably to fit both. And to understand the sensitivity behind, if you're getting vastly different results, then it's probably an indication that your data are very sensitive to the choice of your state-dependent distributions, which you likely don't want them to be. So then you sort of have to think, well, do I really want, does a gamma state-dependent distribution, is it providing the information that I need versus the Weibull or whatnot? It's not an easy thing to do. Okay, I've have the PHM fit showing the first 10 rows. And here's what I want to show you, because this sort of freaked me out for a long time. Remember that for the Poisson HMM, we did not incorporate any orderings. So I didn't say that my lambdas had to go from smallest to largest. They weren't ordered in any way. So what's going to happen is that our theta was our transition probability matrix entry. And in the Bayesian framework, what you typically do is you look at R hats. And you want your R hat to be equal to 1. We spent all that time waiting and look at our beautiful R hats of 2.37, 1.74, 230, and so on. So does that mean that there's something wrong? And I want to point out this LP variable, which is log posterior in Stan. This is actually 1. So our log posterior distribution across the 3 chains is exploring the same area. It has converged, let's say. So if your LP is 1, your R hat's 1, and all the other R hats are not 1, and sometimes there'll be 20, 30. It's okay. Don't freak out. What happened is that there's something called label switching. So maybe across the 3 different chains, your ordering of the lambda values are different. So maybe lambda 1 is the largest value, lambda 2 is the smallest, and lambda 3 is the middle. And in chain 2, it goes lambda 1 is actually the smallest value of lambda. So this phenomenon is common. It's just called label switching. And what you can do, and I won't rerun this now, but go into the Stan code. And I can't move. There we go. Go into the Stan code, and rather than just describing it as a vector, say it's positive and it's ordered, and this will generally resolve your problems. And then you'll have beautiful R hats of 1, all because you're giving it some structure. You're ordering the labels of your lambda values. Okay? So you can just change the way that you define lambda. You can rewrite it, or you could just use also the fits that you already have and just figure out which lambda value goes where across each chain. I think that was sort of the big thing I wanted to point out. And you can also extract, like I said, the states, posterior distributions from the entire state sequences as well. That information is in here. Okay, I can go back to the questions now and finish up.
Yeah, so we have like 2 minutes left or so.
Yeah.
Let me see. I think one last question is, how frequently do locations need to be recorded relative to the number of behaviors you're trying to simulate? Or is the frequency of switching between states more influential to the amount of data you'll need?
Yeah, I mean, it depends on your system. If you have one observation per day, you're not likely to be able to pick up more than likely 2 states, because you're missing so much information between those daily positions. Also depends on the size of your species, difference between an elephant and a small shark, and how they move and how they use the space.
All right. There are additional questions, but probably we won't have time to go over them. Thank you, Vianey. That was really nice. We really appreciate all the effort you put into the presentation. And I think your code is going to be really helpful for everybody.